2.2, higher degree functions. So graphs of polynomial functions that are drawn, they are continuous, which means there's no holes in the curve, there's no gaps, and it can be drawn with smooth, round curves. So you know it's continuous if you can draw the graph and not pick up your pencil from the paper. That means it's continuous. So let's look at kind of a typical f of x equals x to the n. We specify n is an integer. N is greater than 0. And so we know what it's going to look like if n is even. It's going to take the shape of this. If it's odd, like x cubed, it's going to have this shape. And we know that the number of turning points, so we'll say turning points, is equal to or less than or equal to n minus 1. So if n is 2, you're going to have one turning point, like right here. If n is 3, we're going to have up to 2 turning points. This is up to the number of turning points. So if n is 5, you can have up to 4 turning points. But it doesn't mean you're going to have 4. Let's look at this equation here. Y is equal to quantity x plus 5 to the 4th. So it's graphed here, and there's only one turning point, although it's spread out quite a bit. And that's what you get with these higher powers. If you had something else, you could have a 4th term, or let's say f of x equals x to the 4th plus 3x squared plus 2x plus 1, something like that. I don't know what this is going to look like, but I know what it's going to look like on the ends. See how it goes up on the left and it goes up on the right. So this is what these x to the 4th terms are going to look like. It's going to go up on the left and it's going to go up on the right, and it could do anything between. So here we have 1, 2, 3 turning points. Okay, so we're going to talk next about a leading coefficient test. Okay, let's look at the leading coefficient test. And this would be for f of x equals a x to the n. And what we're doing is describing infinity. It's going down. Okay, so that's a test. And this would be for f of x equals a x to the n. And what we're doing is describing the left-hand and right-hand behavior. We want to know what it looks like, and we want to describe what the function is doing as x goes to negative infinity and as x goes to positive infinity. So let's take our first case. A is greater than 0, n is even. What we can see is it's going to the up on the left and it's going up on the right. And so it doesn't matter what's going on in between. We know that there's 1, 2, 3, 4, 5 turning points. So this is going to be an x to the 6th equation. But we want to describe what's going. So let's look on the left. So as x goes to negative infinity, what's happening to the function? So as x is going this way, f of x is going to infinity. So f of x keeps going up and up, going this way. Then on the right-hand side, as x goes to infinity, this way, what's f of x doing? Well, f of x is still going to infinity. Okay, so let's look at the next one. A is less than 0, n is even. So we see what's going on the ends. On the left, for the left end, it's going down. The right end is also going down. So we want to describe this. So on the left, as x goes to negative infinity, we look at what the function is doing. The function is going to negative infinity also. So f of x is going to negative infinity. And we'll look on the right-hand side. As x goes to infinity, f of x is going to negative infinity. It's going down. Okay, so that's a is less than 0, n is even. Let's take our third case. A is greater than 0, and n is odd. So we see what's going on. It's going up on the right-hand side, and it's going down on the left-hand side. So to describe that, we say as x goes to negative infinity, f of x also goes to negative infinity. On the right-hand side, as x goes to infinity, f of x goes to infinity. And lastly, we have our case where a is less than 0 and n is odd. So it's just the opposite of the one above. On the left-hand side, we're going to infinity. On the right-hand side, the function goes to negative infinity. So describing that, we say as x goes to negative infinity, f of x goes to infinity. And on the right-hand side, as x goes to infinity, f of x goes to negative infinity. So this is what we mean by describing the behavior. You're going to say, what is it doing on the left-hand side of the function? What's it doing on the right-hand side of the function? So let's look at an example. So our first example, f of x is equal to 1/4 x cubed minus 2x. So the only thing we're interested in when we're going to describe the behavior of the left hand and right hand is what is a and what is n. So a is greater than 0. I like to abbreviate it. I just call it, so a is either going to be plus or minus. So this is a plus, and the exponent is either going to be even or odd. This is odd, so this is a plus odd. And so because it's a plus odd, we know that it falls to the left. So we would just do that and rises to the right. And this is enough to describe the n behavior. So the next example, f of x is equal to negative 3.6x to the 5th plus 5x cubed minus 1. So we're just going to identify this is a negative and it's an odd. So we know the negative odds rise to the on the left and fall on the right. So we just rising on the left and going down on the right. So that's all you need to do. You can write it out too, but just doing the arrows is sufficient. Okay, a couple of things we know about zeros of polynomial functions. Let's say we had f of x equals x to the n, and this is going to have less than or equal to n real zeros. It can have some imaginary zeros, but it can't have more than n real zeros. It doesn't even have to have any, and we'll look at an example with that. And the other thing, and it has less than or equal to n minus 1 turning points. A lot of times, if n is 4, you'll see 3 turning points, but in the first example I had in this lesson, you can see where it actually only had one turning point. So it doesn't always have n minus 1 turning points. Well, how would it look if we didn't have any real zeros? Well, let's just take an example. Let's say here was our coordinate frame, and we had had something that looks like this. Okay, well, this is going to be, how many turning points does it have? So 1, 2, 3, 4, 5. So this is, again, going to be a x to the 6th. We also know on the ends, if we describe the end behavior, it's going up on the left and it's also going up on the right. But this doesn't have any real zeros because nowhere does the graph cross the x-axis. That's where you have real zeros. And so this particular function has zero real zeros. So let's take a look at an example. Okay, here's an example. We want to find the real zeros of f of x is equal to x cubed minus 12x squared plus 36x, and we want to find the number of turning points. And then we're going to sketch to see what we think it looks like. Of course, we could put it in Desmos or a graphing calculator, but we want to do this manually so we know how to do it. So the first thing we do, we're going to find the real zeros. We have to set f of x equals 0. So 0 equals x cubed minus 12x squared plus 36x. Well, we can factor an x out, and so 0 equals x squared minus 12x plus 36. Now this happens to be easily factored, so 0 equals x minus 6 times x minus 6. And so our zeros, remember the x that we factored out, that's also a 0. So remember, this is, you fix this, this is times x. And so I could put a x there just to carry it. So x equals 0 is a 0, and x equals 6 is a 0. So the zeros are x equals 0, x equals 6. Now, we're going to learn later, we'll talk about multiplicity. See, x equals 6 is a 0 for this one, and x equals 6 is a 0 for this expression. So we actually have two values, x equals 6. Well, we don't write it because it's still duplicated, but what that tells us is something. And here's what it tells us. So let's draw the coordinate system, and we're going to plot the zeros. So x equals 0, that's one of the zeros. X equals 6 is another one. So 1, 2, 3, 4, 5, 6. Now, we also know that this is a x cubed. So this is a plus odd. So plus odd. We know that plus odds go down on the left, up on the right. So we're looking at the 0 points, and the farthest one to the left is at x equals 0, so we know it has to go down at that point. And here, at some point, it's going up, and we know that x equals 6 is another 0, but because there's two of them, what that tells you, it's called a multiplicity of 2. It means that the graph comes down and touches that 0 and then goes back up. It doesn't cross the x-axis, it just touches it and goes back up. And so here we have our plus odd, goes down on the left, up on the right. It has two zeros, and it has two turning points. Two zeros and two turning points. Now, what we don't know is where this vertex is here. Doesn't really matter at that point. It could be higher, it could be lower, but at least we described the shape of the graph, and we know what it does on the end behavior. Okay, so here's the rules for sketching graphs of polynomial functions. Number one, you're going to apply the leading coefficient and exponent test. So is it a plus odd? Is it a negative even? Number two, you're going to find the zeros by either factoring or using a quadratic equation if you have to. And for number three, you can plot some points just so you get an idea where the vertex may be between zeros. And so what we're going to do, let's see, number one. So here's our function, f of x is equal to 2x cubed minus 6x squared. So this is a plus odd. So we know that it falls on the left and it goes up on the right. So that's what our ends are going to look like. So number two, find the zeros. So we set it equal to 0. That's 2x cubed minus 6x squared. So I'm going to factor a 2x squared out of it, 2x squared times x minus 3. So you know the zeros, this is equal to 0, are at x equals 0 and x equals 3. So we plot those. Let's start a graph. And let's say, so here's our coordinate system. We're going to plot the zeros. A 0 at x equals 0 and a 0 at x equals 3. We know it goes down on the left, so we can do that. We know it goes up on the right, and so it does something in between. We suspect that it's going to either go up above the x-axis, or we don't know. So let's just plot, let's say at x equals 1, and we plug that in. So f of x equals a -4. So it's going right here. And at x equals 2, f of x equals -8. So 2, 2, 4, 6, 8. So we know it goes here. We don't know if that's the vertex or not. So let's look at how many turning points we can have. Well, it's going to be less than or equal to 2 turning points. So we can probably guess that it's going to do something in between here. I'm going to say it's going to do this, come down, and it doesn't look very pretty, but you kind of get the idea of what it looks like in between the zeros. Okay, our last example, we're going to sketch f of x is equal to -1/4 x to the 4th plus 3/2 x cubed minus 9/4 x squared. So the first thing we're going to write down, this is a negative even. And so we know it falls to the left and it falls to the right. And n is an x to the 4th, so we're going to have less than or equal to 3 turning points, TP. Okay, next thing we do, we try to factor this or make it a little simpler. So let's factor out a negative, set it equal to 0. We're going to factor out a -1/4 x squared out of this. So this is going to be x squared minus 6x plus 9. And that looks pretty factorable. So we know this, because this x, one of the x's is equal to 0. And let's factor this term. Well, this is a x minus 3 times x minus 3. So we have a, at x equals 3 as a factor. There's a multiplicity of this, of 2. But also, if we go back to this term here, we can factor an x out of that, and that's going to give us 2 x's. So we could factor it's a -1/4 x, negative 1/4 x, and another x. So looks like we have a multiplicity of this 0, multiplicity of 2. So there's really 2 zeros and two zeros at 0 and 2 zeros at 3. And so we know what's going on, or we think we do, because of the multiplicity. So let's go ahead and give us a coordinate system. And we want to graph it. So let me do a straight line here and here. First thing we do is we identify, or we put in our zeros. So we have 0 at x equals 0 and at x equals 3. And we know that this is rising, or going down on the left and going down on the right. So this is going down on the left, and it's also going down on the right. But we also know that it doesn't get above the x-axis, because 2 zeros at x equals 0 means it just touches and then goes back down. And likewise at x equals 3, it just touches the x-axis and comes back down. So if we were to plot points like x equals 1, we get, let me just do an xy table, since that's what we like to do anyway, xy table. So let's go at x equals 1, y is negative 1. At x equals 2, y is negative 1. So here's our points, 1, negative 1, and 2, negative 1. So it looks like we need to figure out what's going on between x equals 1 and x equals 2. So put in x equals 1.5, and I didn't calculate it out, but we know it's going to go kind of down a little bit. So it has to, so let's fill in the rest of this graph. So at x equals 0, it's going to touch, come down, and it's going to go down a little bit, and then up, and then down. So this is what it's going to look like. How many turning points? 1, 2, 3. So we're good. We found the turning points. We found the zeros. We sketched it. Now the vertex here at the bottom, this is a local minimum at x equals 1.5. We didn't get the value of it. Could have, but in this case, since we're sketching it, it doesn't have to be perfect, versus if we're graphing it, then we would want to actually find this value of y and put it in. Okay, well, that does it for 2.2.